Hello everyone. In this video, we are going to solve some questions using Fermat's little theorem. So what Fermat's little theorem says, we checked in the previous video that Fermat's little theorem says if a and p are two co-prime numbers, if a and p are two integers which are co-prime to each other and p is a prime number, then with the help Fermat's little theorem says that a to the power p minus 1 is congruent to 1 mod p. A to the power p minus 1 is congruent to 1 mod p. This is the statement of Fermat's little theorem. Now with the help of this Fermat's little theorem, we will just solve some numerical questions. So for example, question number 1 says, find 3 to the power 31 mod 7. Find the value of 3 to the power 31 mod 7. So first we will check, can we apply Fermat's little theorem? Let's say this 7 is p, this is a. Is p a prime number? Yes, p is a prime number. 7 is a prime number. So p is a prime number. And a is congruent to p? Yes, because GCD of 3 and 7 is equal to GCD of 3, 7 is equal to 1. So it means we can apply Fermat's little theorem. So when we apply Fermat's little theorem, it becomes 3 to the power p minus 1 is congruent to 1 mod p. A to the power p minus 1 is congruent to 1 mod p. So what is 3 to the power p minus 1? 3 to the power 7 minus 1, which should be congruent to 1 mod 7. So 3 to the power 6 is always congruent to 1 mod 7. So what does it mean? 3 to the power 6 mod 7 is equal to 3 to the power 6 mod 7 is always equal to 1 mod 7. And what is the value of 1 mod 7? Which is 1. So now we will try to solve with the help of, now we have one thing, that 3 to the power 6 mod 7 is equal to 1. With the help of this 3 to the power 6 mod 7, we will try to find out the value 3 to the power 31 mod 7. So 3 to the power 31 mod 7. So we can write 3 to the power 31 as 3 to the power 6 5 times and then 3 mod 7. So this is 6 into 5, 30 plus 1. So 3 to the power 6 mod 7 is always equal to 1. So we need to only find out the value of 3 to the power mod 7. 3 mod 7. And what is the value of this 3 mod 7? It comes out to be 3. So we can conclude that 3 to the power 31 mod 7 is equal to 7. So this is how with Fermat's little theorem we can compute remainders of large numbers. Let's solve one more example. The second one says, to find out the value of 2 to the power 35 mod 7. So 7 is a prime number. Yes, 7 is a prime number, and let's say 7 is p and 2 is a. A is congruent to p, 2 is congruent to 7. Yes, because GCD of 2, 7 is equal to 1. So now we will write Fermat's little theorem. A to the power p minus 1. So 2 to the power 7 minus 1 will be congruent to 1 mod 7. So 2 to the power 6 will always be congruent to 1 mod 7. So 2 to the power 6 is equal to 1. Whatever is 2 to the power 6 mod 7 will be 1. Now we can write 2 to the power 35 like 2 to the power 6, 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 and then 2 to the power 5 whole mod 7. So every time when we apply mod 7 to this, it comes out to be 1. So it will be 2 to the power 5 mod 7, which we can write 32 mod 7, and which comes out to be 4. So our answer is 4. So we can say 2 to the power 35 mod 7. So it reduces a lot of calculation and it gives us some remainders for large powers. But we need to check two things. First thing is p should be a prime number and a and p should be co-prime to each other. Then only we can apply this Fermat's little theorem. For example, you need to find out 2 to the power 1000 mod 13. So it's a large number, but with the help of Fermat's little theorem, we can solve this with 2-3 steps. So this 2 is a, 13 is p, and a is co-prime to p, we can say, and p is also prime. So it means 2 to the power 13 minus 1 will be congruent to 1 mod 13. So it means 2 to the power 12 is congruent to 1 mod 13, or 2 to the power 12 mod 13 is equal to 1. So what we can do? We can similarly we can find out the value for this. How many times? So it will be like when we divide 1000 with 12, it comes out to be 84 and the remainder is 4. It goes 84 times completely and remainder is 4. So we can write 2 to the power 84 into 2 to the power 4 mod 13. So here we can write it is like it comes out to be 1 and it comes out to be 16. So it will be 16 mod 13 and 16 mod 13 will be equal to 3. So the answer is 3. So this is how we can apply Fermat's little theorem in different solving different remainders. For example, we need to find out 2 to the power 30 plus 2 to the power 30, 2 to the power 30 plus 3 to the power 30 plus 4 to the power 40 plus 5 to the power 50 plus 6 to the power 60 mod 7. We need to find out this value. So 7 is p, which is a prime number. It is congruent to 2 because all are p minus 1, congruent to 3, congruent to 4, congruent to 5 and congruent to 6. So it means we can write 2 to the power p minus 1, which is 6, is congruent to 1 mod 7. 3 to the power 6 is congruent to 1 mod 7. Then 4 to the power 6 is congruent to 1 mod 7. Then 5 to the power 6 is congruent to 1 mod 7. And in the last 6 to the power 6 is also congruent to 1 mod 7. So we will try to find out this. So remainder is 2. When we divide 30 with 6, remainder is 2. So it is 2 to the power 2. It is 3 to the power 0. When we divide 40 with 6, it comes out to be 4 to the power 4, 5 to the power 2 and 6 to the power 0. And it means it should be mod 7. So it will be 4 plus 3 to the power 0, 1. It will be 2 to the power 8 again, and it will be 25. It will be 1 mod 7. So 2 to the power 8 means 2 to the power 6 is again 1. So we can write 2 to the power 2 here in place of this. Then 25, then 1 and then mod 7. So it comes out to be 4 plus 1 plus 4 plus 25 plus 1 mod 7, which comes out to be 35 mod 7. 35 mod 7 and 35 mod 7 is equal to 0. So answer is 0. So this is how we can solve different type of problems with the help of Fermat's little theorem when we need to find out the remainder. But just we need to check the condition. The last question which I am going to discuss in this video is, let's say question says find all integers x such that x to the power 86 is congruent to 6 mod 29. X to the power 86 is congruent to 6 mod 29. So from Fermat's little theorem, we know that x to the power 28, which is p minus 1, is congruent to 6 mod 29. X to the power 28 is congruent to 6 mod 29. So it means we assume that x and 29 are co-prime to each other. Okay, so we apply Fermat's little theorem here. So now when we write x to the power 86, it will be x to the power 28, then x to the power 28, 3 times x to the power 28, and then x square. It is congruent to 6 mod 29. Because it is given that it is congruent to 6 mod 29, so we say that x and 29 are co-prime. So now it will be x square is congruent to 6 mod 29. So but x square is congruent to 6 mod 29. Then what should we write here? X square is congruent to 6 mod 29. So when we say x square is congruent to 6 mod 29, so it means the remainder should be 6. When we multiply x square by 29, the remainder should be 6. So in which case the remainder will be like power 2 remainder will be, so when we multiply 29 with 2, it comes out to be 58, and 58 plus 6, it will be 64. So x square is equal to 64 mod 29. So we can write x square minus 64 is equal to 0 mod 29, and it will be x minus 8 and x plus 8 is congruent to 0 mod 29. So x should be equal to 8. The value of x can be 8 and x can be minus 8. So here we can write the value of x can be like x is equal to 8 and x is equal to 29 minus 8, which is 21. So this is for two values of x. This comes out to be for two values of x to the power 86 will be 6 mod 9, because it can, when we write 0 mod 29, so either it can be 29 or it can be 0. So if we put it 0, x will be 8. If we put it 29, x comes out to be 21. So for two values of x, the value of x to the power 86 will be congruent to 6 mod 29. So these are some examples of Fermat's little theorem, uses of Fermat's little theorem. We will use all these theorems in encryption schemes when we study DES or AES. These all will come in use, and our next assignment will be based on the questions related to these theorems. Thank you.